Good morning, everyone. Yes, my name is Fatima MEITE, and I will talk about the bioremediation of agricultural soils polluted with pesticides, thanks to biocomposites, which are carrier materials recovered with biofilms and modified in surface with chemical modifications to help the growth of biofilms. This research is made for this context, for a context of agricultural application of pesticides on agricultural soils, which leads to important concentrations of pesticides in the environment, like shown with this chart, with this presentations of concentration of pesticides in groundwaters across the French territory. This is a threat for the human health and ecosystem quality. Several solutions exist to remediate soils with chemical, for instance, chemical remediation, but it is also possible thanks to biological remediation. And across the biological remediation that occurs, we can use bioaugmentation thanks to the presence of biofilms on carrier materials. This is interesting because in such a way, microorganisms will be more resistant to stress, and a better remediation could be obtained. This is also interesting because we can tailor the surface of materials to improve the formation of biofilms, which will occur after the attachment of microorganisms and their proliferation on the surface of materials, which can be improved. So thanks to the nature of these materials and their characteristics on surface, with a change of the charge of the materials, of the weightability, the roughness, and so on, we can improve or, on the contrary, change the interaction of microorganisms with the surface and then have different biofilms characteristics, let's say. I talk about surface modifications of carrier materials, and in this project we choose to recover the carrier materials with layered double hydroxides, which are compounds made with a layered structure. The layered are composed of calcium and iron hydroxides, and we can have the presence of water molecules and different anions between layers. Such materials can be obtained by co-precipitations. Co-precipitation of two kinds, mainly. Three. Co-precipitations obtained after the mix of sodium hydroxide solutions and calcium and iron nitrate solutions in such a way that we have an increase of the pH during the reaction or a decrease of the pH. We will have some little difference in the characteristics of the layered double hydroxides, and we test these two protocols during this research. The aim of this work is to answer to these questions. Do the nature of the carrier materials impact the final bioremediation that will be made? Can we have a difference in the bioremediation efficiency according to the age of the biofilm? And does the surface modifications that were applied improve the bioremediation? In my presentation, I will talk about the experimental setup, then the material and surface modifications that I made, and the biocomposite efficiencies, and then comparison and stress important factors and conditions. I worked with three Karine materials. Oyster shell that was rounded, pozzolana, and zeolites. You have three pictures of these different materials. These materials are calcium carbonate for oyster shell and aluminosilicates for the two other materials. I talk about surface modifications. So I made layered double hydroxides in presence of the different materials. This is made in such reactors with a double envelope, let's say, to control the temperature thanks to an apparatus that sends water at the appropriate temperature in the reactor. So this is made with the two protocols that I described. And after that, we sieved the suspension obtained to be able to determine the nature of the oxide that was made. And this is made thanks to X-ray diffraction. And we also try to attack all the compounds obtained at the end. So the Karine material with the layered double hydroxide on it, and assess the concentration of calcium and iron thanks to atomic adsorption spectroscopy, in order to be also able to know the recovery efficiency that we made. After that, on modified and non-modified materials, we try to grow biofilms. This is made in a mineral salt medium that contains MCPA, an herbicide, that will be studied during all the procedure, but is also the carbon source for microorganisms. And we introduce a bacterial consortium as inoculum. The efficiency of the procedure and of the formation of biofilms is checked thanks to the remaining concentration of MCPA in the solution, thanks to UV visible spectroscopy. After that, we can at least begin the real interesting experiment, which is to test the efficiency of the biocomposites in a liquid medium, also the mineral salt medium, and in soils, which is the aim of this procedure. So the biocomposites, modified or not, are introduced in a mineral salt medium with a concentration of MCPA at 5 micrograms per liter, or we introduce these biocomposites in a sandy soil, and we applied a concentration that is 90% of the recommended dose in agriculture. Then we check the remediation efficiency with the measure of the MCPA concentration in the solution or in the soils after leaching, water leaching, to access to the concentration of MCPA that is remaining in this soil. After that, I also tried to characterize the microbial community thanks to DNA extraction, PCR, and TRFLP. Let's talk about the materials and the modification. Here you have pictures of the three materials, so oyster shell, pozzolana, and zeolites. You have raw materials first, and then materials obtained after the modification thanks to for the attempt to cover them with layered double hydroxides. The first protocol with decreasing pH, so we started with the sodium hydroxide solution, and we added the calcium and iron solution to be able to form layered double hydroxides, or the inverse protocol for the second protocol. Here you can see the X-ray diffractogram of the phase obtained after we sieve the suspension. I said that we have to do so to be able to check that we formed layered double hydroxides and not other things, like can happen if the mix of the layered double of the sodium hydroxide and the calcium ion solutions are not made its appropriate flow rate. We can, for instance, only form ferrohydrate, which is a simple ion oxide and not a layered double hydroxide. So we have to check the nature of this phase before any other experimentation. And this succeeds. We form layered double hydroxides. with a rate, covering rate about 3–4%, except in the second protocol for the oyster shell.
So we can speed up,
okay.
So we can have some time left to
okay. Here you have the dissipation of the MCPA obtained in the medium salt, in the minimum salt medium after 4 weeks of biocomposites production. You can see that we be able with such biocomposite with that age, I can say, to dissipate MCPA in solution. You can see the difference with the control, which is the solution without addition of biocomposites. You have there's charts that present these results for 4 weeks old biocomposites, 7, and then 10. We always obtain a DT50, which is the time to remediate the 50% of the initial MCPA, of the initial pesticides, about 1 day. I did the same in soil, and we can see here that the dissipation is not complete. We finish with about 20% of MCPA in the soil, but this procedure is interesting because the dissipation is higher, is faster than in a control soil without addition of biocomposites. I did it for with the 4 weeks old biocomposites, 7 and 10. Here this T50 is about 12 days. And we do not have the same behavior. We have in the solution worst dissipation for oyster shell, while here this is quite the inverse. I tried to look, to compare conditions and to be able to see if that's a different age of biocomposite, different carrying materials, or different modification will improve the bioremediation, what would give the best results. So I look all the DT50 and try to compare them according to these conditions. And what we can see is that only the carrying material really change the dissipation behavior. Behavior. So that's it. And I tried to look for the 10 weeks old biocomposites, what are the microbial communities present. So I made TRFLP and only compare the different aspects of the microbial communities, and we can see differences. Here you have results for, at each time, oyster shell, pozzolana, and zeolites for raw materials, and after the different modifications. And we can see differences, especially in the pozzolana and zeolite systems. Next steps will be the characterization of this community to be able to see if we have genera able to degrade MCPA or involved in the degradation of other pesticides or not at all, and be able to better understand the carrier material importance in this dissipation. Thank you.